So, real quick review from yesterday. Newton's first law. It's the law of inertia. And what Newton's first law says, remember, is that objects will maintain their velocity unless they're acted upon by an outside force. Right? The middle school version of it that you learned was an object at rest stays at rest. An object in motion stays in motion unless acted upon by an outside force. And what we added to that was an object in motion stays in motion at the same speed in a straight line unless acted upon by an outside force. So your speed and your direction are velocity. That's why this is a more precise definition of inertia than what you guys learned in middle school, right? Or whatever other science class, probably. So an object will maintain its velocity unless acted upon by an outside force. So now, what is it called when you have a change in velocity? Can someone type it in the chat or just shout it out? When an object has a change in velocity, what do we call that? I'll give you a hint, right? It starts with an A. Oops. Yeah, thank you. It's acceleration. Remember, the equation for acceleration was change in velocity, delta V, divided by t. So basically, you guys, Newton's second law deals with forces and inertia and changes in velocity. It basically it comes directly from Newton's first law. So Newton's first law says that an object will maintain its velocity unless acted upon by an outside force. What Newton's second law is going to say is that if you apply a force to an object, you will produce an acceleration. That's what the law says. So let's look at it. So defined like as by your book, Newton's second law says an outside force applied to an object will produce an acceleration. And that's if the overall force acting on the object is not zero. So if I apply a force to an object and I have a net force other than zero, the object will accelerate. Okay. Now, we're going to talk about net force some more in 1 second, but I want to give you an example. So let's say that I have like a really, really, really heavy box. Okay. Let's say it's like, 10,000 newtons. That would be over a ton. And I'm here and I'm trying to push on this box. Okay. So that's me. I'm trying to push on this box. Now, I probably won't be able to move it, right? So if I just think about me as an outside force pushing on this box, the first part of Newton's second law says an outside force applied to an object will produce an acceleration. I can push on this box all day. I won't be able to budge it unless I can apply a force that pushes it in this direction that's bigger than the force of friction. Because everyone here knows in real life that friction is a force. And it acts between any two objects, right? So if friction here was, say, 1,000 newtons, that means that in order for me to move this box and to accelerate it, I would have to push it with at least, like, say, 1,001 newtons. That was supposed to be a 1, not a 4. So let's just say it was a 4. If I push with 1,004 newtons, friction's pushing against me with 1,000 newtons, the overall force, or the net force acting on that box, it won't be zero, and I will accelerate. But if I don't push harder than friction, I won't be able to accelerate the box. So the overall force, the one force that replaces all the other forces acting on the object, it has to be bigger than 0. Can't be 0. So really quick, let's talk about net force. So in real life, there's always more than one force acting on an object. Okay, in real life, there's always friction, or there's air resistance. So there will always be forces that are trying to make an object go faster, and always forces trying to make an object go slower. All right. The net force is the one force that replaces all the other ones. Now, the one vector that replaces all the other vectors, we call it the resultant, right? And force is a vector. So the net force is the same as the resultant force, or it's the vector sum of all the forces. All of those words mean the same thing. So the vector sum of all the forces is the resultant force. The resultant force is the net force. So if I were to look at this box, let's say this box is being pulled 10 newtons with a 10 Newton force in this direction. It's being pulled with a 30 Newton force to the right and a 12 Newton force to the right. What would be the one force that would replace all of those other forces? Can someone shout it out? So I have 10 newtons pulling to the left, 30 newtons pulling to the right, and 12 newtons pulling to the right. What is the one vector that would replace those 3 vectors? Okay, so someone wrote 52, and that is a good thought, right? But you're thinking about these as scalars and not vectors, right? Remember, when we do vectors, we add them head to tail. So if I were to pick them up and move them, oh, I think I can't do it because I grouped them together. But let's say if I were able to pick them up and move them, I would have 30 newtons. That would be 30. Then I would have 12 newtons. And then I would have 10 newtons, right? And the resultant force would be from the very beginning to the very end. How long would that vector be? And the answer is 32. That's right. So this net force here would be 32 newtons. That is the one force that would replace all of the other forces acting on that object. So if I had a 32 Newton force, and by the way, direction is important. So if I had a 32 Newton force pushing to the right, that would be the same as having a 30 Newton force pushing to the right, a 12 Newton force pushing to the right, and a 10 Newton force pushing to the left. So this is the one force that would replace all those 3. So once again, net force, one force that replaces all of them.
Why'd you put the arrow going right? Isn't it right?
No, well, because this force is acting to the right. Do you see it? And this one's acting to the right. These add up to 42, right? Correct? And that only adds up to 10. So it would be 42 to the right direction minus 10 to the left. That leaves me 32 to the right. Does that make sense?
No, not really.
No? Well, okay, I want you to think about this here. Let's think about it in a slightly different way, all right? Let's think about a tug of war team. Okay? So there's me. You guys haven't gotten to see me, but I'm a little round. Okay? And here's one of you. All right? Now, there's a rope between us. The tug of war rope. We'll have to make that a different color. So we're both pulling on this tug of war rope. Okay? Now, I'm pulling with a force of 100 newtons. Right? It's a tug of war, so I'm pulling to the left. You're pulling with a force of 200 actually, I want these numbers to come up. You're pulling with a force of 300 newtons. So you're 3 times stronger than me, right? And you're pulling to the right. You guys all know how a tug of war works, right? Correct? Okay. Um, would I win this tug of war? Would I pull you to the left? Or are you going to win this tug of war? Are you going to pull me to the right?
I'm gonna pull you to the right.
You're going to pull me to the right. And so the direction of the final force is going to be to the right. And then the amount of that final force, the magnitude part of the vector, that's going to be 200 newtons. Because you pulled with 300 to the right, I pulled with 100 to the left. The one force that could replace those would be 200 newtons, and it's going to the right because that's how you're pulling me.
So the one that has more like newtons, that's usually the way that's gonna go.
That's right.
Okay.
That's right. So in this case, there were 42 newtons pulling to the right and only 10 to the left. So this box will move to the right. So the force is to the right.
Okay, got it. Mhm.
Okay. Now, here's another situation where I have a skydiver. This skydiver, he has a weight of 800 newtons, and I don't know. Well, you guys, I think, are all still too young probably to go skydiving, but there's a point when you're skydiving when the force of air resistance matches your weight. So if I have air resistance pushing me up with 800 newtons, and my weight is pulling down with 800 newtons, what's the net force?
0.
It's 0, right? It'll be 0 newtons. That's not supposed to say on. It's 0. We're going to talk about why I keep saying newtons in 1 second. Oops. But the reason I keep saying newtons is because that is the unit of force that we'll be using. You guys are probably used to using what as your unit of force? Nobody knows what English unit for force you always use? Yes, it's pounds. Thank you. So pounds is the English unit for force. Newtons is the metric unit. We're always going to use the metric unit. So
Wait, when it's 0, that means that there's like no acceleration.
That's
of
it.
Force.
Yeah, that is exactly right. So when the net force is 0, right? If we go back to Newton's second law, Newton's second law says that in order for there to be an acceleration, the net force or the overall force acting in the object cannot be 0. So in this case, and we were going to go back to this, but we might as well say it right now. In this case, when you're skydiving and your weight and air resistance are exactly the same, the net force is 0, that means you're not accelerating. Does that mean that you stop in midair and just like float there? Do you think if you jump out of an airplane, there's a point where you just start floating above the earth? You know, I could see people that have their cameras turned on, they're shaking their heads, right? Like that's just, that sounds crazy, because it is crazy. The fact that you're not accelerating does not mean you're not moving, right? So this is something that's called terminal velocity. When a skydiver hits terminal velocity, it just means that the force of air resistance matches their weight, so the net force is 0, and there's no acceleration. Whatever speed they were moving at, they'll continue to move at that speed. So if that speed was 100 miles per hour, they'll keep moving at 100 miles per hour. If it was 150 miles per hour, they'll keep moving at 150. And I don't know if you guys have watched movies where they have skydivers, but do you think you can change that terminal velocity? Do you think you can alter how fast you're going as a skydiver? Yeah, and a bunch of people said yes. The way you do it is you change the amount of air resistance by changing your body shape. If you want to go slower, you put out your arms and you put out your legs and you have a bigger surface area. That increases air resistance, so it'll decrease your terminal velocity. If you want to decrease the air resistance so that you're moving faster when this happens, like you keep your arms in, you make yourself like a missile pointed at the ground, right? Then you'll go faster. You're not taught to skydive like that, by the way. So, you're taught to do this, what this guy's doing. All right. So let's talk a little bit more about Newton's second law without equations yet. So one of the things about Newton's second law, you guys, is that it says that the net force that you apply to an object is directly proportional to the acceleration. So the bigger the force that's acting on the object, the bigger the acceleration. The smaller the force that's acting on the object, the smaller the acceleration. Now, like you could think about it this way. When we get out of class, not before, right? Because you want to pay attention. You turn on the Sox game because you want to see like a winning team in Chicago, right? So you turn on that game. Tim Anderson, if he doesn't want the ball to go very far, so he's going to bunt the ball, he applies a really small force to the ball. He just kind of holds out the bat and barely touches it with the bat. When he does that, the ball won't go very far. Because small force is a small acceleration. Now, if he wants to hit a home run, what he does is he takes a huge swing. He uses his legs, he uses his whole body, right? He follows through, and he's going to apply as big of a force as he can to make that ball accelerate at as high of a rate as possible, to try to make it go as fast as possible off his bat and leave the stadium. So home run swing, big force, bigger acceleration. A bunt swing, small force, small acceleration. Big force, the ball goes far. Small force, it doesn't. Like, you guys know this stuff, right? You know it because you live life. And you know that if you apply a big force to something, you make it accelerate, you make it move fast. And if you just apply a little force, you don't. So for all the juniors who will be taking SAT this year, and for all the seniors who haven't taken it yet but will be, I want you to think about what that graph looks like. So if I was going to graph force versus acceleration, if they're directly proportional, that's a math term, what does the graph look like?
Wouldn't it be linear?
It's going to be linear. And which direction does it point? Does it point down from left to right? Does it point down, or does it point up from left to right?
Up, left to right.
Yep, it does. So the graph is going to look like this, where if the force is big, the acceleration is big. If the force is small, the acceleration is small. All right? This is a graph for a directly proportional relationship. I guarantee you, when you take the SAT, or even if you do the ACT, which I would recommend you guys take both actually, you will see questions that ask you to graph, right, these types of relationships. So these should be easy questions for you, right, when you see them. Okay, so force and acceleration directly proportional. Now, what about mass? The mass of an object is going to be inversely proportional to the acceleration. All right, this is what I want you to think about. I've got 3 different vehicles. They're broken down on the road. And you and I we're driving and we want to be good Samaritans, so we both pull over and we're going to help these people push their vehicle, right, out of the way, like to the service station. Which of those is going to be easiest to push?
The sedan car.
Right, the sedan. It's not a trick question, right? So this mass is the smallest, right? So this mass is the smallest. This mass for this box truck, this mass is the biggest. You know, and this is somewhere in the middle. So it would be easiest for us to push this car. You've probably seen someone doing this, right? Pushing a car into a driveway, into a service station. Okay. This van, especially if it's flat, we could probably push it, right? But we could push this one a lot easier. So our muscles are our muscles. They can provide the same force, but this car will be able to accelerate at a higher rate. This car will accelerate at a lower rate because it's bigger, the van. And this box truck, we actually may not even be able to accelerate it because we may not be able to produce a net force bigger than 0, right? So the more massive the object is, if you provide the same force, the acceleration is smaller and smaller. Does that make sense to you guys? Okay, that should make sense because you live your life on the planet Earth, and that's just the way things are, right? Actually, and so if we were to graph that relationship, so if we were to graph mass and acceleration, assuming that we're pushing the object with the same force, what does that graph look like if it's inversely proportional?
Wouldn't it be the other way from like top to bottom, from left to right?
Yep, it would be. So in this scenario, you guys, if I have a big mass, I'll have a little acceleration. And if I have a little mass, I'll have a big acceleration. That's what inversely proportional means. So the larger the mass, the smaller the acceleration. The smaller the mass, the bigger the acceleration. And once again, we're assuming that we're pushing the object with the same force. So now that we know that force and acceleration are directly proportional, and we know that mass and acceleration are inversely proportional, and we know that a net force other than 0 is going to produce an acceleration, we could actually write Newton's second law as an equation now. You guys have the math skills to do it on your own, although I'll show you what it is. So this would be the summary of Newton's second law, right? Net force other than 0 will produce an acceleration. The acceleration will be directly proportional to the force, and it'll be inversely proportional to the mass. So if I were to look at an equation, and you guys, you don't have to worry about scribbling all this down, right? I'll send you this. I'll link this to our document like I always do. If I were to write this in an equation, this is what the equation would look like. That the net force is equal to the mass times the acceleration. And if I were to write it out with just our symbols, I would write it out like this. Oops. I would write it out at, I forgot I had that silly. Okay, I'm ready now. I'm sorry. I would write it out as force net, the net force, equals mass times acceleration. Most of the times when you see this equation, people just assume that you know this is the net force, and so it's just written out as F equals ma. I want to make it really explicit though for everyone. that you know it is the net force. All right. So F equals ma. This is probably the second most famous equation in physics, you guys, behind E equals mc squared, right? So FMA, F equals ma. It's a pretty important equation. It's been around for a long time. Now let's talk about units here. And you could be writing all this down right on your equation sheet with all your other equations. So the mass, in physics, we always measure mass in kilograms. And for acceleration, we always measure acceleration in meters per second squared, or meters per second per second. So if these are in kilograms, and this is meters per second squared, then the unit for net force will be a kilogram meter per second squared. Now we have a shorthand way of writing kilogram meter per second squared. It's named after the person who came up with this whole thing. And a kilogram meter per second squared is called a Newton. And we abbreviate it with a capital N. So if you see like 10N, that means 10 Newtons. So remember that, you know, the Newton is just a shorthand for a kilogram meter per second squared. Mass times acceleration. And from this equation then, you can see how force and acceleration are directly proportional because they're on opposite sides of the equation. So if one gets bigger, the other one has to get bigger if we keep mass constant. And you can see how mass and acceleration will be inversely proportional because they're on the same side of the equation. So if I keep the answer the same, if I keep the net force the same, if one of these gets bigger, the other one has to get smaller. So when things are on opposite sides of the equation, when one gets bigger, the other gets bigger. When they're on the same side, when one gets bigger, the other one has to get smaller, assuming that you're keeping the other variables the same. Okay? So far, so good? Any questions before I go on to the next slide then, you guys? No. Okay. So there's one more equation that I want you to have, and that's another equation for net force. All right. Now, in this class, in honors physics, we're only going to deal with forces that are acting in the same plane, right? Along the same axis, I should say. So we'll always have forces that are acting along, like, say, just the x-axis. And if that's true, there are forces that try to make the object go faster. We'll call those applied forces. Some books also call them accelerating forces. And there are forces that try to make the object go slower. So we'll call those opposing forces. You'll sometimes see them referred to as decelerating forces. So applied forces, you guys, these are forces that are trying to make the object move faster. Opposing forces, these are trying to make the object move slower. There is one force. You know, most forces could be either applied or opposing, depending on the situation. Sometimes when I push a car, like in our example before, if I'm trying to help someone push a car like to their driveway, I'm applying a force. That would be an applied force. But if let's say my car was parked in my driveway and I forgot to put the brake on and I got out of it and it started rolling down the driveway into the street, I might run to my car to try to stop it, right? That would be an opposing force. Not that I've ever done that before, right? So most forces could be either applied or opposing depending on, like I said, the situation. There's one force that always will be an opposing force. It's the F force, the F word. Does anybody know what it is?
Friction.
It's friction. So friction, you guys, will always be an opposing force. Friction is always trying to make objects slow down. All right. Air resistance as well. Air resistance is kind of a version of friction. So friction is always an opposing force. We're going to talk more about friction tomorrow, probably. If we don't do the lab, we'll talk about friction. So these are our two equations. Net force, mass times acceleration. The net force is also all of the applied forces minus all of the opposing forces. Now, if you guys... Yeah, I'm sorry, what?
Oh, my bad.
No, that's fine.
So negative F opposing, is that just a force, or is that friction slash wind resistance right there?
It could be friction. It could be wind resistance. We could go back. Here, I'm going to go back all the way. Let's go back to this slide right here. All right. When we look at this situation with the box, these two forces, since they're bigger than the one on the left, these will end up being applied forces. This one will end up being an opposing force. Why? Because these two forces are going to pull the box to the right. So they're making it go faster, and this force is just making that box go slower. So these are the applied forces, this is the opposing force. It doesn't necessarily have to be friction. It could be that there are 3 ropes tied to this box and I have 3 people pulling on it. Right? Or in my tug of war example, you pulling with 300 newtons, you would be the applied force. I am pulling with 100 newtons, so I'm slowing you down. I would be the opposing force. Does that make sense? Good. All right. What else did I want to say about that? No, I think that's it. All right. So far, we just have these two. These are going to be our only 2 new equations. Now, if you guys decide to do AP Physics, then they're going to apply this as well. But their vectors won't only be on the same axis. Their vectors will go off in different directions. And then you'll have to find the net force along the axis of travel. But, we're not there yet. If you guys take AP Physics 1 next year, you'll get to see that. Or if you take engineering physics in college, or a scientific, if you do a scientific field and have to take physics again in college, you'll see that as well. All right. So let's see how this translates to a problem. Let's do a problem. So I have a box. This box might look familiar to you. And these forces might look familiar to you. So I have a box, and the box is going to accelerate at 1.5 meters per second all right? Or 1.5 meters per second squared. Now, it has 3 forces acting on it, right? I want to know, what is the mass of this box? So I know the acceleration, I know the mass, and I know these 3 forces, okay? Now we have a brand new equation that says that the net force is equal to the mass times the acceleration. Well, I know the acceleration, I'm looking for the mass, I need to figure out this net force. Well, we just did this, right? We just said the net force is going to be all of the applied forces, I'm just going to call it FA, minus all of the opposing forces. Well, if I look at this box, Someone just tell me again, which way will the box move? Will it move to the right or to the left?
The right.
It's going to move to the right. So it's going to accelerate to the right, which means that these two forces are the applied forces. So I'll have 30 and 12 as applied forces. And then 10, that's making it slow down. So the net force would be 30 plus 12 minus 10. That will be 32 newtons. We did that already on the other slide, right? So now I plug that into my equation here. 32 newtons equals the mass times the acceleration, 1.5 meters per second squared. I want to get rid of that 1.5. It's being multiplied, so I would divide. The 1.5s will disappear, right? And can someone punch that in their calculator? What would be 32 divided by 1.5?
$21.3.
21.3?
Yeah.
Oh, I messed it up. I said 20. All right. 21.3. And my units would be kilograms. So are there any questions on this problem?
I have a question. So I'm actually when we write F and CT, could we just write FN?
Yeah, of course. Yeah, you could write. That's supposed to be NET, not CT. I'm sorry. So it's FNet is what I wrote. But you could just write FN for FNet.
And then are we usually gonna use both of those equations, or is it just this problem?
Well, so it'll depend. It'll depend on the problem.
Okay.
All right. Let's do another one. I think in today's problems, I did. I may have used it in every one, but I'm not 100% sure. So let's look at this one. So in this one, I have a student. They have a mass of 100 kilograms, and they're being pushed by a friend while they're sitting on a skateboard. This is actually when we're in school. In a normal year, this is something we do. It's one of our labs. In fact, in one of the physics classes, we even made the skateboards.
One of my friends sent me a video of you on the skateboard going down a ramp.
Yeah, that was it was fun. Did I look scared?
Kinda. It looked like you were gonna hit into the kids, but then you leaned over and you made it through.
Nice. All right. So I have a student here, you guys, on the skateboard, and they have a mass of 100 kilograms. Okay. They're being pushed. They're being pushed by the friend, and they're accelerating at 2.5 meters per second every second. And the acceleration will be in the same direction we're being pushed. Okay? I want to know two things. I want to know, first of all, what is the net force that's acting on the object? And then I want to know what is the force that's being applied to me over here by my friend if the force of friction between the skateboard and the ground is equal to 35 newtons. So the first part, the part that's going to be easiest, is to find the net force. Net force is equal to mass times acceleration. I know my mass, it's 100. I know the acceleration, it's 2.5. I could punch that in my calculator, or I could do a little bit of mental math and know that's 250 newtons, or 250 kilogram meters per second squared. That's the net force. Now, that net force is going to be equal to the applied force minus the opposing force. So I know that the net is 250. I already know that. I don't know how hard my friend pushed me. So I don't know what the accelerating force was. But I do know what friction was. It's 35. Oops. It is 35. My pen just went crazy on me. Sorry about that. So the force that I'm being pushed with, $35 newtons. There we go. So I want to get applied force by itself. How do I get rid of this 35? Right now it's being subtracted, so I would add it. So I'll add it to both sides. Those will cancel. And I'll get that the applied force is equal to 285 newtons. So that's how hard my friend is pushing me. So the force, the one force that replaces all the forces would be 250. And my friend is pushing with 285. Friction is pushing against him with 35. Good so far? Okay, I want to do another one. I think we might just have, oops. I think we might have time for just one more problem, okay? And before that problem, I have a special public service announcement. Weight and mass are not the same thing, okay? So if you're given an object's weight is a force. It's the force that you're being pulled towards the center of the earth with. And mass is just how much stuff is inside of you, okay? And I'll give you an example of this. If I came up with a business plan, and my business plan was to charge people $1 million, so it's got to be rich people. I'm going to charge people $1 million, and I'll tell them that I'll make them lose almost 40% of their body weight, and they don't have to diet, and they don't have to exercise, nothing. Like they just show up, and I'll make them lose all this body weight. Now they give me the $1 million. I put them in a rocket ship. I bring them up to the moon, and I have them stand on a scale. Will I have fulfilled my end of the deal? The answer to that, you guys, is I will, right? Why? Because gravity is less on the moon. So your weight is the pull towards between you and whatever, planet, moon, whatever you're standing on. That pull on the moon is less. So that person, though, won't be any skinnier. They probably won't be any happier unless they like the view, right? But I will have fulfilled my end of the bargain, right? So your weight is always equal to your mass times gravity. If you want, you could write that down on your equation sheet. And if you think about it, you guys, that is a fancy way of saying that weight, which is a force, is equal to mass times acceleration, because gravity is the acceleration of gravity, right? So your weight is mass times gravity. Your weight is mass times 9.8. Now the reason I'm telling you that is because this problem is going to have weight, okay? For this problem, let's just do part A. We're not going to do part B. If we have time tomorrow, we'll do it. So I have a 100 Newton scooter. That is not the mass of the scooter. That's the weight of the scooter. So the weight of my scooter is 100 newtons. The mass of my scooter would be 100 newtons divided by the acceleration of gravity. Is it okay, because we're running out of time, is it okay if I just round gravity to be 10? Will you guys be all right with that? Okay, so mass, I'm going to make mass equal to 10 kilograms. It would be 100 divided by 10. All right, now this scooter, it says it's starting at rest. So its original velocity is 0 meters per second squared. Then it says that its final velocity is 5 meters. Oh, did I write per second squared? I just meant per second. Sorry about that. So its original velocity is 0 meters per second. Its final velocity is 5 meters per second. And it's traveling just 2 seconds worth of time. Now the force of friction, which will be our opposing force, that'll be 6 newtons. I want to know what is the applied force. So if I were to draw a little picture of this, here's my scooter. The scooter has a mass of 10. Okay. It has a frictional force of 6. And it has some mystery applied force that I'm pushing it with. That's my question mark. Now I know that F net equals mass times acceleration. I know the mass, but I don't know the acceleration. Do I have what I would need to solve for acceleration though? I know you guys are smart enough to know the answer is yes to that. So with this information, I would probably use the equation acceleration is final velocity minus original velocity divided by time. Now remember, I told you can't forget your old equations. We'll be using them all year, right? And so this will be 5 minus 0 divided by 2. The acceleration will end up being 2.5 meters per second squared. So now, if I want to figure out the net force, that would be the mass, which is 10 kilograms, times the acceleration, which is 2.5 meters per second squared. Then the net force is going to end up being 25 newtons. I know that the net force is equal to the applied force minus the opposing force. So I would say 25 newtons equals the force that I'm applying minus friction, which is 6. This is being subtracted. So you would add it to both sides. That will go away. And the applied force ends up being 31 newtons. Now I know we did that really fast, you guys. You could go back and look at the video if you want to see it slower, and we'll talk about this more tomorrow. But this problem was a 3-step problem, but you guys are used to doing those types of problems now because we did them for projectile motion, right? These problems are becoming easier for you.